when we are trying to control a system, I think one of the easiest ways to think about this is, let's say that you have, you're driving a car. Okay, this is my terrible view of where you're sitting, you're driving the car, right? So you're manipulating, okay, so in front of you there is the road, so you're trying to stay on the road. You are turning this thing called the steering wheel, and you're trying to play this video game, right, where you have this handle in front of you and you're trying to stay on the road. I'm going to take that system apart a little bit and try and say what exactly is happening. There's obviously the person who's making the decisions about where the car is going. And for our purposes, we're going to draw a little box around that decision-making process. And the kind of coded word that we're going to use for this, and that the textbook uses for this, is called a control law. Now, one of the major differences between doing this just using your brain and building a box or a machine that will do this is that we typically have very little introspective ability to understand our own decision-making process. Big words. What I mean is you would find it difficult to write down an algorithm or an equation that exactly describes the way that you approach driving a car. I think most of you who have ever done anything in the world and then tried to write a computer program that does the same thing have encountered this difficulty, that many of the things that we do, we don't really have conscious access to the exact steps. It's really one of the major challenges of learning how to program computers, is to become conscious and aware of the thoughts or the unconscious processes in many cases that lead to the decisions that we make in the real world, and then be explicit about writing them down. Now, all of the stuff in that box, you will be pleased to hear, everything that's inside of the decision-making control law box for this semester, we will completely ignore. Okay? So everything that is about the decision-making or devising control laws, we will address in CPB. Okay? Now, when you're driving that car, you as a person, you're sitting in the driver's seat. You are making your decisions based on things that you observe about that car system. So there is a flow of information that goes into that decision-making process from the system, which in this case is a car. Okay, nobody taught me art when I was in school. I'm an engineer, not an artist. Okay, so that's my terrible approximation of a car. Okay, so we are making our decisions based on our observations of the system. We are then translating whatever those decisions are into actions that act upon the system. In this case, we turn the steering wheel, we step on the pedals, and so on. And that then causes the system to change. And so we then go back like that. Now, in control terminology, if we were to zoom in on this piece here, right? When we're talking about control, we would say that the actions that we take that have an effect on the system are called manipulations. And these things are called measurements. And so, because engineers like being lazy, most of the time you'll see people abbreviate that to manipulated variable, or MV, and the measured variables, in most cases, we are measuring a very specific variable called the controlled variables. And what I've drawn here, you will see that it has this kind of cyclic nature. In other words, I make a decision, I manipulate, the system reacts, and I measure. I make another decision, or I make simultaneously a decision. This circle is known as a feedback control loop. And the feedback part comes from this idea. I've drawn the system in this order very specifically because I've written from left to right the way that we will attribute cause and effect in this system. I can make that a little bit even more clear by putting these arrows on the other side. So let me just restate that here. So from the system point of view, we will also in many cases call these things inputs and these things outputs. And one of the things that students really struggle with in this module is this idea of distinguishing the causal relationships in systems. I'm going to try and get you to a place where you really understand the difference between relationships and causality. So remember that we started out talking about a car. And our larger goal in the whole of the subject is to eventually replace that person in the green box with a mathematical equation or a computer program in the green box. But first we will need to understand more clearly how those decision-making processes work. And in fact, the most important thing in making decisions is to be able to predict the result of your actions. So let's ponder that for a moment. It would be impossible to drive a car or ride a bike or even just make basic decisions about the world in general when you are trying to make decisions if you had no way to know what would happen if you did something. If it was completely random, right? So if you turned the steering wheel to the left and the car teleported 5 meters to the right, right? How would you play that game? If you couldn't rely on reliable effects following from things that you do, you couldn't make decisions, right? Making decisions, making control decisions, involves doing things that you predict will have the effect that you're looking for, right? So I want to unpack a little the kinds of problems that we can think of within this little box diagram that I've shown you over here, right? So we have a system, and remember, we're talking about a real system like a car or a bike or whatever, right? We have things that make the system do things. These are the manipulations. These are things like steering wheels or the angle of the handles in your bike or anything like that. So these are actions that are going to change the system in the future. And then we have ways of measuring whether we are achieving what we want to achieve, right? And typically, we have targets for controlled variables, right? So we want to stay in the middle of the road or in, at some position on the road. We want to maintain a particular speed. The things that we want are the controlled targets or the set points for the controlled system. Okay, so to a certain extent, what a control system is doing is it's saying, you want me to do this, you want the system to do this, I'm seeing it do this. I predict that if I change the steering wheel, you want me to turn left, I predict that if I turn the steering wheel to the left, the car will go to the left. And so I'll do that action, see whether that had enough of an effect, maybe correct a little bit and so on, but that's the whole process, right? And the problem is that in many cases, we've been solving equations that look something like F is equal to ma. Okay, and you may imagine that there's this relationship where I can say, okay, I've got all three of those variables in this equation, and so far, it's always been easy to understand what you're solving for and what to do by saying, well, there are knowns and unknowns. Up to now, your problem-solving process has usually involved saying something like, right, I have, if you give me M and A, I can tell you F. If you give me F and A, I can tell you M, and so on, right? So it's like, if you leave one out, I can work out the last one using the equation. And the equation doesn't care, right? The equation doesn't care whether you write it in the form F is equal to MA, and I'm just going to be explicit about this. I can write this in many different forms. I can write this as M is equal to F over A, and I can also write this as A is equal to F over M. Right? So those three different versions of the equation are equivalent mathematically. They represent the same equality relationship, and there's no implied, no one variable there is any better than any other variable, right? And solving this problem, when you did physics, this was kind of how you generate new problems, right? You have a certain equation, and then you solve the equation, and then you leave out different pieces of information, and you test yourself on how well you can kind of isolate that one that you're missing. So you haven't really been thinking about what causes what. And in fact, in an equation like F is equal to ma, it's not really clear. We can't really say that the mass is causing the force, or that the force is causing the acceleration, without more information about the system like a picture, right? Now, this is a general rule, and I'm saying this here because it's not in the textbook. Up to now, you haven't really been thinking about causality, but in fact, there is an arrow of time. And I would like you to become sensitized to the idea that one of your first clues into what is a cause and what is an effect is to look at what happens first in time. It seems so obvious, right? But it is a really deep fact about the universe that we know that it is impossible for things that come after something in time to be the cause of that thing. Right? Does that make sense? So if we think about a timeline, right? I flip the light switch, and then at some later time the lights turn on. Right? In time, flipping the light switch happens before the lights turn on. If you slow down time enough, right, you'll see me moving very, very slowly towards that light switch, and like click, and then there's a little spark, and then the electrons start flowing through the circuit, and then the lights slowly kind of glow into light. And that's the way time works. And that's how we know that it's not the other way around. It would be silly to say, oh, when the lights came on, the light switch flipped. Right? It's not that way around. And the way that we know this, the prime way in the light switch example that we know this, is because the lights come on after the light switch flips. So the first kind of rule of causality is that causes come before effects. In time. Now, there's another piece of the puzzle here, which is a little bit more subtle, but if we were getting really deep and philosophical about it, it would be kind of some thermodynamics principles, right? So when you thought about thermodynamics, there are people who say that's kind of almost the definition of time, right? So time, the way that you know, like if I played you a video, everybody knows you can play videos backwards and forwards, and sometimes it's quite hard to discern whether, I'm sure everybody's seen somebody like taking a video of themselves walking backwards and then playing it forward, right? Like, and sometimes it's hard to know. Like, you can't really tell, is time moving forwards or backwards? But it's super easy. If you see a glass break, right, or something fall off a chair, right, it's super easy to know, oh yes, this is forward. The braking part is forward. Why? Because entropy is increasing in that direction, right? So it's very, very unlikely, weirdly, technically possible, right, for a glass. So it is actually possible for kind of these shards of a glass to kind of self-assemble back into a nice glass, right? This is actually theoretically possible. I'm sure you did this in thermodynamics, right? Like given the right circumstances and like if you shake it enough, like it's something that could happen. It's just so unlikely that we effectively think that it's impossible. Why? Because it's much easier to increase entropy even in local systems than it is to decrease entropy in local systems. So the natural direction of things is towards disorder and like equal temperature distributions and all the kinds of things that you learn about in thermodynamics, right? So the second kind of thing is entropy increases. And I'm writing that one bullet point down there, but you have to understand that you have to now fill this in with a whole lot of additional examples from your thermodynamics classes. So if you think about all the things that you know, why does diffusion work the way that it does? Like if I open a perfume bottle here and everybody smells the perfume after a while, that's entropy, right? And so again, it would be weird if I had some kind of a smoke bomb and I opened up the smoke bomb over here and what happened is you saw all the smoke just like gather itself together and like go into the bottle. That would look strange. Not impossible. It's a perfectly possible version of events. There's nothing stopping, literally nothing theoretical stopping the molecules to bounce around and like bounce all the way back into that container. Right? You learn this in thermodynamics, where like you do the math and it's like, yes, okay, well, it's possible, I suppose. It's just not very probable. And so we reason in these two different ways about cause and effect. So when we and the textbook has this convention which I'm going to follow, which is when I write equations. Right? So originally I said equations have no causality. So these are all equivalent. But by convention, I will try most of the time to write equations so that the cause is on the right and the effect is on the left. Right? And so what I'll try to do is, if I write f is equal to ma, that will be a strong hint or a strong clue that I'm expecting m and a to be known at the time when I'm trying to solve that equation, and I'm expecting to then want to calculate f. Now, I want you to understand that this is completely conventional. So the math doesn't force you to obey causality rules, because equations fundamentally are not causal, because we can kind of solve for any unknown that we want. This whole idea of causality, probably this is the first time in your course that you've really come across the idea that you should be thinking about cause and effect in this way. It's the number one stumbling block in this part of the work. So don't be too hard on yourself if it doesn't feel clear quite yet. But I want you to have that primed in your brain before you start looking at the modeling equations, because the modeling equations, weirdly, like knowing how to do math, most engineers are awesome at knowing how to do math. You've been doing a lot of math so far, and you've come through all the way until your third year, you know, so like you're probably really good at it. This is new. So this is a control problem that most of us have encountered in our lives. And I would like you to to look at this picture, and I've identified a couple of variables here, right? So you can see that I have the temperature and flow, two taps, a hot and cold tap. And I'd like for you to take a little bit of time, redraw this image just locally, think for yourself which of these things would be manipulated variables and which of these things would be controlled variables within this control problem. We're going to walk through this table, right? So I'm just going to have you raise your hands if you said that temperature was a manipulated variable. Nobody. So did everybody say that temperature was a controlled variable? What about flow? Did anybody say that flow was a manipulated variable? Flow is a controlled variable, right? Now, I just want to stop there for a second, and I want to challenge you and make you think about, in a certain way, I am changing the flow, right? The person in the shower is actually having an effect on the flow. And it can feel sometimes as though moving the tap is the same as changing the flow, right? So moving the tap happens simultaneously as to the change in flow, as near as we can tell, right? But it is causally in front of the flow. So in other words, we wouldn't say, oh, look at that, there's more water, and then like look at it and like see the tap turn. That wouldn't happen, right? But think about it. Why is that true? Is that true because of one of the previous rules? Because we couldn't tell, right? The flow is changing at the same time as the tap is turning. So how do we know? How do we know it's not the flow causing the tap to turn instead of the tap causing the flow to change? Yes?
We need to actually manipulate the tap. There must be an external input to turn the tap.
That's excellent. I love that. So there are certain variables, right, where we have a strong intuition that they cannot autonomously move. They cannot move without external intervention. And so that's one of the other rules that we can use to tease apart the direction of causality, right? We can reason about, would this thing be able to change by itself? Now, a lot of things that are built specifically to be handles have this property. So you can basically think anything that is designed for a human to interact with as a handle is automatically a good candidate to be an input into the system and a manipulated variable, right? So the steering wheel example is a great example of that. These taps are a great example of that. So you can use that as a shortcut. And you can say, but wait, it's a switch. It's designed to be turned on by a person. So it couldn't, or normal kind of dumb switches don't just turn themselves on and off. It gets weird when you start thinking about smart switches and that kind of stuff. Every year it gets harder to talk about this stuff. Right, so now exactly for that same reason, sorry about that, it looks like everybody has converged on the idea that the hot water and the cold water are manipulated variables. And so the last little bit of testing here is, who got the direction of causality as going from the person to the taps? In other words, going from the person to the taps, and then going through all the way here, then through the person, all the way back into... So that's the control loop, right? The system, remember, and we just have to remind ourselves that in this subject, we will never consider the person to be part of the causal chain. So we always think about the system as everything except the controller or the decision-making process. So once we've masked out the person making the decisions, the only piece of the arrow that is left is the causal direction, going from the taps to the flow and the temperature. Does that make sense? Now I want you to think about this while you read through the textbook sections that are on ClickUp,